Now presenting is the hack Good Enough, Vojislav Milivojevic.
Thank you. First of all, thank you everybody for coming. I know last night was Rakia workshop, so it's nice that you're here. So the presentation is called "Is the hack good enough?" Maybe that's not the exact question. The exact question you need to first ask yourself: what do I want to do with the hack? So then, is that my hack good enough for that? Is it for research, for prototyping, for some product? So what I wanted to talk about today is basically, is the hack good enough to make some commercial product? So if you have a hack, can you make it to the product? So first, who am I? My name is Vojislav. Many knows me as Voja. I'm, as it said, almost master engineer because I need to finish my master thesis. This is just a small push for me to tell you that and to finish it. Just need to write the thesis. So I'm also open source hardware and software engineer, trying to push some open source projects into the world through the GitHub. You can find many interesting things on my GitHub page. You can find it there. And as, let's say, most important thing, I'm a research and development engineer at Institute IRNAS. So I will tell you about it more a bit later. So when I was writing this presentation, I was also starting to read one interesting book. You're probably familiar with the book. It's a new book. You can find it in stores. But the first sentence of that book is, anyone who cannot understand that a useful science can be built on a stunt hacking will not understand this book either. So this is also meant for this presentation. So anyone who cannot, just slightly different, anyone who cannot understand that a useful products can be built on a stunt hacking will not understand this presentation possibly either. So what will I talk today about? First, I will introduce where do I work, what do I work on. After that, I will show you what was that first hack and how we began to build this product and what is that product. Then discuss some design choices over the years and how we came here where we are now. And after that, just a bit of how my organization and I see open source in hardware. It's a bit different than software, not too much, but there are some differences. After that, finishing with the lessons that we learned over the years, and then I want to share that with you to get this process easier for you when you do such thing. Some small Q&A session, and the most important session for me, I mean the part of the presentation is that you come here and see the prototypes, touch them, break them, do whatever you want, and ask me personally what you want to find out. So I am, as I said, a research R&D engineer at Institute IRNAS. It's a non-profit research and development organization based in Maribor, Slovenia, but we also have an office here in Novi Sad. This is where I work. So we are working on some our research and development projects, and also projects for some other organizations, companies. But I will focus on one of our products today, the research and then the product. But I will mention some others. Also there is just behind our office in Maribor, there is a fabrication lab called Fabricor. Basically the same people, but that fabrication lab basically makes all the weird stuff we are developing and researching on. Some of our main projects, some of them are main at the moment, some of them were main at the past, are VitaPrint. It's a 3D open source bioprinter. basically a 3D printer with a nozzle that puts gluten and those kind of stuff out. It's a new thing. You can read about it on GitHub and our blog. Very interesting stuff. Symbiolab is an open hardware biolab. Basically, we want to make all those equipment that is used in biolabs open source and easy for people to have and access, because it's for some reason expensive equipment. Goodenough CNC, it was affordable manufacturing toolset based on 3D printer and CNC that can fit in a suitcase and be shipped everywhere in the world. This is what we did in the past. It's not something that we are currently producing, but again, you can find all the details on the GitHub. It's interesting stuff. And one that I skipped is KORUZA. It's a wireless optical communication system, and that is the thing I'm going to talk about today, and all the phases from the research, actually from the hack to the research, and then to the designing it, to manufacture it and producing it. So this is how it looks like when you begin. Basically, tape, glue, and everything you have in your lab. So if you have an idea, try to build it as fast as you can with things you have in your office or you can buy and get in a few days. The thing is, you don't need something that is working exactly what you want at the beginning. You want something that is just a slightly working and if you get that result, then you should move on. If you don't get that result, you should move on, but not with that project. Think of something else. I will get back on this picture to show you what was that first hack. So first, to explain what I will talk today about is, this is a KORUZA. It's a open source, open hardware wireless communication system. Basically, like you see on this picture, you have two units shooting laser at each other, and at distances 100 to 150 meters, over 1 or 10 gigabits per second. Basically, it's a wireless optical cable. So the main reason to producing this was to overcome some gaps in the especially big cities, urban areas where you have a lot of Wi-Fi and you have a problem with congested spectrum with the radio signals. So you see this problem also on some big conference like CCC, Maker Fairs, where you never have a fine Wi-Fi connection. So it's the same in the big cities. So this point-to-point communication can overcome some gaps, like stepping over the street and expanding your actual optical fiber communication network. It's especially interesting because sometimes in these cities it takes a lot of time and a lot of money just to put the cable under the road. The goal is eventually to put that cable under the road and have everyone have fiber to the home, but until then, this is, I think, good solution. This is just a picture showing how we imagine to use this system. Like I said, light speed networking, no cables, no congestions, and 10 times cheaper. That is what we want to achieve, because in the past these free space optic FSO systems existed, and when you say FSO, that meant $10,000, $20,000. They were really expensive, and that was mainly because of the equipment, and the parts they use were custom parts. So that is always expensive. So this is a nice picture of timeline, how we did it. It started in 2012 from an interesting idea. It started basically all over the world, from London, Kyrgyzstan, and Slovenia. The interesting thing was we started, it was a research paper at the beginning, then evolved through some phases and generations of prototype. And now this is in 2016, not the last one. You will see also the last one, but that was the last one for the testing. As it says, we kind of pioneered the use of commonly available parts to create low-cost effective solution, and in a minute I will tell you about that. So here we are back at the first prototype. So just the tape, glue, and some spare parts. This gray box which you see here is a media converter. You're probably familiar with it. So it's basically you have a power, you put Ethernet cable in, and on the other side you get the SFP module connector, and the SFP module is a thing which converts electrical signals to optical signals. The thing we realized is, okay, let's try to use SFP modules without optical cable. Is it possible? So we put this together. This golden thing on the top is a green laser for pointing, and the black thing is just a lens for collimating the beam. And this first prototype could do it for 1 second at 1 gigabit per second over 100 meters. And that was enough for us to continue. So basically, after putting it together, it all broke down because it was not usable. But then we realized, okay, it's a nice time. We have now 3D printers, nice little things. So let's use that and like a glue for all those parts. As you can see here, just few 3D printed parts, and now we have something that is working, but it's not something that you can reuse actually, because it wasn't that stable, but it was good enough to prove that this device could work longer and more efficiently. Well, we 3D printed some parts and thought, okay, this 3D printing is nice, so why don't we just 3D print this device? And we did that. And don't do that. That's the point. Because if you want to 3D print a big chunk of parts, it never ends up well. You spend too much time, and at the end you need to adjust them and put them together, fit them nicely, especially for the precise products. And that's not good. So again, it was just evolving phase. We learned from it and go on. This 3D printing technology was really interesting for us. So we say, okay, let's try to build our own 3D printer. We liked all the 3D printers, but we didn't like, because some of them had some parts that you can only buy from manufacturers. So if you want to build it, okay, you can buy everything at the internet or anything, but still some dedicated parts you needed to buy from them. And that was not okay for us, so we built the 3D printer that you can basically build anywhere because it was commonly available parts. And this was, then we learned that we need to use as much as more commonly available parts to get this product really cheap. So while we were designing and building this 3D printer, it was nice because we learned some things and saw some things that we could use actually in our new prototypes of the KORUZA. For example, these spring couplers were great. As you can see, they now connected the motors to shafts in our different product. Like that previous picture, sliding brushes from Troublemaker, our 3D printer, were also implemented into one of the prototypes of the KORUZA unit. And that's the thing, try to use some of your ideas from other products in your current product they are working on. So after some time, here is where we are. Now we have a prototype that is ready for testing, that is stable, that is working nicely, and we can configure it easy and change all the things that we see that need to be changed. So this here is the KORUZA 1.0. We had a fully modular mechanical design, enables easy modification for variety of use cases, improved stability, reliability, 3D printed part design in OPET's CAD environment. Not a good idea again, but you will see. Interconnections with stainless steel rods, as I said, automatic alignment and tracking, and available as do-it-yourself kit. Because we were doing this as an open source project, we had this interesting connection with many universities that did FSO systems. So we really learned from them because they saw what we do and they could see the design and everything that we did, and they had really nice suggestions what we can improve. So this is one of the aspects of the open source that is really good. You can talk about your idea. So now we have this stable version. We want to test it. We need to prove to people that this works as it should. So you need to write some research papers. First, we needed to see that this beam is reliable, and so we built the beam scanner. Basically some electronics, and again, we're back. We had the 3D printer. Why don't we use the 3D printer for this nice movement to measure the beam strength? You can see on this picture how we did it. Also, here you can see some of the papers we did over the years trying to prove this technology is really efficient and work. At the end, we did it with the papers, but what about the practice? Build the test network. So we built a test network in Maribor with, I think, 10 links working between each other, creating a network, and people had internet over these units. One thing we noticed, they're not, you basically need to have optical visibility to have signal, and that's okay because between the buildings you probably won't have something stopping you from that except some birds, but that packet loss you have in your Wi-Fi also. And some problems could occur with snow, fog, and rain. After a while, we saw that snow and the rain are not that problematic because even in a dense snow and rain, you can still see basically at these 100 meters. And because of the parts are really big, it's not a problem for signal to go through with the full strength. But the fog could be a problem because, you know, the fog, few meters, you don't see anything, and it's really dense. And there are a lot of small particles. So how to test the fog? Again, do it yourself, build a fog tunnel. So we find a factory, 50 meters long tunnel in an old factory, you know, FAP was made there. So basically we built the tunnel, you can see it here, with the cover, plastic cover, have some fog machines to produce fog and test it. Again, write a research paper, and we saw some rule of thumb that if you can see that other spot you're looking for, or that other unit, then you can basically shoot at twice as that. So this was good enough for us to say for this particular distance up to 140 meters, this will work in any case. Okay, this was finished, so let's sell this. Does anyone want to buy this? And this is, let's say, professional product, because somebody who wants to buy this is probably some operator or internet provider or something like that. But when you come and say, okay, we have a really cool open source project, they say, oh, open source, okay. Then you say, oh, you see all the design files, it's 3D printed, really cool. Oh yeah, 3D printed, nice. And they don't call you back. So we then realized we need to build a real professional product that is designed for manufacturing and Again, easy for them to set up, easy to maintain, cheap to produce. That's for us. And we realized we need 1 and 10 gigabit version, but I will talk about also that a bit later. So we started building the final product that you can see on this picture. Like I said, 1 and 10 gigabit version, we had a 1 gigabit version with our previous system and it worked fine, but we thought about it. You know, you have radio links at 1 gigabit. They're decently priced, a bit expensive, but they're okay. But 10 gigabit versions are really expensive. And what we thought about it and what we need to actually change to have this 10 gigabit version was only the laser module, which will cost few more euros. But so here we could have a real advantage of the radio, over the radio. So the thing we needed to do was to put that 10 gigabit port on the outside to provide it. So again, we had a 1 gigabit link. You can see it on that picture. That's 2 PCBs with a SATA cable. And the SATA cable was connection between the media converter and the SFP laser. So how to do it that fast? To try if we could provide that 10 gigabit link. Okay, just modify a bit what you have. Again, buy some coaxial cables, solder them, and try it. And it's working. Great, now we can proceed. Do not do some experiments trying to do something impossible. First try it if you can with what you have. And these coaxial cables were nice, but they were a bit expensive and a bit rough, couldn't bend as we need them. So how to do that cheaply again? Flexible cables. Nice thing, we can move them as we want. We can put differential pairs with a special impedance as we want. But how to connect that to our board? And that was a big problem. You will see this here. I have some, at the end I have some prototypes. It was a few months of work trying to get this working. Because you can have rigid to flex PCBs, but they are expensive. And at the end, we figured it out. So we basically made a sandwich. You have a rigid PCB. On it, you have a flex PCB. And the SMD connector is soldered on that, flex PCB. And over that, it comes the cage, which holds everything together. Well, now we have our own, let's say, rigid to flex PCB, which is working great. So when you're building a product like this, you need a custom hardware. First, we thought, okay, let's buy some platform. For example, like this MQ router. It was open source. It had some chip that had some documentation, but not that good. But we will try it. We build our own a bit complex driver for it. And then, as we iterate, we understood that this is not the way to go, because we always need to try really hard to implement new features, because we didn't have good support for this, and it was really slow and painful process. So what do? You move to something you're really familiar with. So the probably most familiar platform at that moment for us was the Raspberry Pi. But the Raspberry Pi, it's how it is. You can't modify it really. You can put a hat, but then it's getting bigger. And we couldn't fit it inside. It didn't have everything we wanted, and that was the problem. So the Raspberry Pi Foundation has a really nice and neat thing. It's called the Raspberry Pi Compute Module. Now you have three versions of it. So basically, it's this is a SODIMM 200-pin module, just like DDR2 memory, and you have all the GPIOs from this Broadcom chip put out on this header. So now we have a custom hardware working with something we know and it's well supported, and now development is going much faster. So there were a lot of these kind of hacks in our product. While again, I will mention this open source perspective because we can freely talk to people and tell them what we do. And that was really a big benefit for us because they always had great ideas and suggestions. How could we improve it? And if they use it, what ports or interfaces should they have? So this is the way why we this is why we had actually camera inside. So you can log into the unit and see the other unit on the unit on the other side and react quickly if there's a problem. So when we started to build this camera interface, oh, we need zooming something, the unit is far away, how to do it? Okay, go to the Chinese store next door and buy the first lenses you find. We did that, put it together, it's working. And now, in a latest device, we find those Chinese manufacturers, contacted them, and now they're working custom stuff for us. You can also see here the interfaces for the units, some testing bed, also some version of our custom electronics, and the custom electronics for our motor driver. So through all this process, we encouraged open source, and it was really a nice thing. But at the end, like I said, when you come to big companies, they say, okay, it's really nice, but thank you not. Then we really thought about it and talked to some smart people and realized we need to take a different approach. So when we come to our partners, to our collaborators, first thing we try to say to them is what benefits they have while using this open source technology. So we come up with 3 main benefits. It's total ownership, future-proof, and collaborative design. Basically, this is a copy slide from one of our blog posts when we realized that, and it's really well documented, so I wanted to read it to you. So openness comes together with total ownership, allowing full use and repair of existing products as complete eSite info operation is available. So basically, if the company is broke and doesn't exist anymore, they can still use this equipment and they don't throw it away. It ensures the devices are future-proof since they are designed and documented such that the users are empowered to innovate, explore, and upgrade them outside the original specification. The lifespan of the device is expanded, their reuse encouraged, and their open hardware documentation enabling component and communication between all parties involved. And also about the collaborative design, it also simplifies collaborative design, bridging the gap between the development, manufacturing, and use of the devices, enabling evolution of the product to be optimal for everyone involved. So basically, if you want some custom stuff done on this project and somebody other want it, you both have both features. And that's the really good advantage of it. So, the conclusion. One of the main conclusions, and that's why it's this big, is to iterate fast. When you're doing it, try to make it with stuff you have it around you, or you can buy it fast, iterate fast, and push your products forward. And through each of these iterations, some of the lessons and guidelines for open hardware design were expect unexpected uses and support them, because you never know where they will let you. Modular is to simplify, because if you are putting like same connector everywhere, or you have a similar interface, you can always reuse those components and have, again, rapid prototyping of some other products. Always add as much as you can debugging features, so it will simplify your life. PCBs are cheap, so don't make them smaller. that's the case when you don't have to really make them smaller. But again, I didn't put it there, but again, silk screen, it's a thing you read on PCBs, all those letters. They are not paid by each letter, so documentation, put it as much as you can on the PCB. Document each iteration so you can learn from it, and you can really, really learn a bunch of stuff from those documentations. And use serial numbers and checklists. They will, again, make your life easier. So thank you very much. If you have any questions, you can ask them now or later, because after this Q&A section, please come here to see all the prototypes and we can discuss them.
Right. I don't know what the output power of the laser is, but what are you doing for eye safety?
Yeah, this laser is around 3 milliwatts, so, and it's eye safe, and it's in range of 1,300 and 1,500 nanometers, and that is also in the range where it's much safer for the eye, for the signal not to get behind the first surface of the eye.
Hi. Yes. Did you foresee the case of anybody else trying to, perform the denial of service to the receiving device? For example, if somebody else flashes another laser and effectively blinds the receiver with a bogus signal, trying to prevent the communication between those two units.
Okay, I understand. Well, basically, this device is just a fancy cable, you know. You put your data in, it's layer 1, you get your data out. And this connection between is safe because, first of all, you need to be really precise, because this beam is 3 centimeters wide. You need to be really precise to find that beam between these two units. This is the first thing. Then these units, I will show you just a sec. So you see also one big lens. This is for transmitting and receiving data. The one smaller lens underneath it is for the camera. And the two lenses are slow baud rate links, so the units can talk to each other. So if the units don't talk to each other, they know something is wrong. So they will say to you and send a notification, okay, there's a problem, somebody is jamming you or something is happening. So it is pretty safe. If it's happening, you will know it right away, and probably that person, not probably, surely that person cannot receive that signal because it's too small. Okay.
Okay, first of all, thanks for the presentation.
Thank you.
And the question I have is about this production unit, because you said that during the development you had the unit which had a modular design and which was, how to say, made for customization and for adaptation, modification, and so on, actually for development. And I mean, does the same principle still hold for the production unit? Because usually in production you optimize the design. So
yeah,
make
exactly.
It smaller.
It does not. It does not. Because this unit, it's again open source, and you can modify it still. And we left some ports and stuff so you can really modify it. But it's not meant. It's meant for use. Again, we left that modification, how to say, possibility to ourselves also, because we had a lot of questions. Can we modify this device for some other use for some companies? And this is why we left that modification possibility, but it's meant for manufacturing. So we need to reduce cost and make it, again, use widely available parts, but fit it to our need. And you can still buy the configurable version for testing and researching. And that's how we try to put those two together, let's say.
Yeah, so actually you're also offering the modular version for...
Sorry?
You're also offering the modular version
Yeah, it's a scientific-like version. So
okay.
it's nice because there are a lot of universities which do free space optics, and it's a good test platform for them.
Okay. Sorry, can I have another question? Just a quick one, because you said that on the market of these optical transceivers, you have also other vendors which offer the same solutions, but on which are more expensive. So
yeah.
Would you say that the cost was lowered down by the open source design,
Yeah.
or what are the main points? If you could maybe reiterate or explain to making this your product cheaper compared to the other?
Well, I think the main thing was that first hack. So basically, these SFP modules, they produce them in millions. It's the most, not the most, but the common thing when you come into the server room or something like that. So if you have that, and that is the most expensive part, believe it or not. So in all those other products, this receiver and transmitter optical is most expensive part. So this is the thing where we managed to lower our price really down.
Okay, well, great. Thank you for answering.
Thank you.
So you said that it's impossible to receive the communication from the beam,
Yeah.
but in a fog situation, the lights get scattered by the fog. Isn't it possible to read it from the scattered light?
No, not really, because maybe I'm not the right person to answer this question because I didn't do the research about the light, but I will get back to you on that for sure. Just leave me the contact after.
Hi. First, congrats on this excellent product. It looks really great, and the specs are also amazing. You mentioned something about contacting operators.
Yeah.
Could you please tell us more about your experience with getting the product on the market and the obstacles you faced? So a little bit more on that.
Yeah, this phase is also currently, at the moment we are doing that. So it is hard because when you're doing a telecommunication equipment and you're not a big company, it's a problem because these big companies, internet service providers, they want your equipment in their labs for a year or half of a year, and you need to provide it to them so they can test it and say, okay, it's okay for us, we can use it. So I can't tell you really much about it because we can't tell some of our contacts at the moment because they don't want to tell it. But it was interesting. We find out that these kind of systems are not used, but they need them in some strangest places on Earth. So, one of the examples is a radio satellite. So you basically, in the middle of nowhere, you have a bunch of antennas, and you receive the radio signals and make some radio image from the space, and you need to connect those antennas, and you can't use any kind of radio because it will disturb your really low signal strength. So there's a bunch of these kind of examples, and that was the good thing about modularizing our design, so we can change thing or two for their needs, like customization of our current product.
I have a question also. Okay. Haven't you found your product on AliExpress yet?
No. Yeah,
I mean, it's open source, and I know that all of the open source hardware you can find on AliExpress, eBay, and so on.
Yeah, that is a problem. But first thing, this is a complicated enough product for Chinese to put time in to reproduce. It doesn't have. It's not something that you will go buy on eBay. or AliExpress or wherever. So you need to have contacts to sell this. That's another advantage. And if they do that, it would be great because it would be then it would be more cheaper and we could produce more cheaper and sell it. So that's the thing.
Any more questions? Yeah.
You said you're operating as a non-profit. Yep. So how do have you structured this as a separate company to sell this?
Well, not yet. But as I said, there is a Fabricor, which is a fabrication lab, which sells all the products we produce and actually makes them and sells them because it's a company. That's the one non-profit and one profit organization.
Any more? Okay. Thank you for a great talk.
Thank you for all the questions.